students, now let us solve this question. Find the S parameters or otherwise S matrix of n by 1 ideal transformer. Consider R01 is equal to R02 is equal to R0 reference impedance it is given. Now this is the transformer, ideal transformer given, small n by 1. Even if n1 by n2 is given, you know how to convert that ratio. Now what to do? First you redraw this one. Whatever diagram is there, you redraw this one. So this is port 1. This is port 2. Redraw that. So after redrawing the diagram here like this, okay, this is I2 and this is V2, this is V2 and what do you say, this is I1, this is n is to 1. Now start the discussion, students. I told you for testing purpose you take the source, that means high frequency voltage signal generator you take. Then after taking here, I am connecting that here, VG1 I am connecting here. This is port 1, no? Before port 1 I have to connect. Then it will have some impedance. To that impedance, you may connect some other impedance. In such a way, the overall impedance becomes R0 to that one. So that is nothing but that R1 is equal to R0 we have connected. Now it is given connection to this one. Similarly, here it will have some load impedance practically, but you do some adjustments in such a way here overall impedance becomes that is R2. So that R2 is nothing but R0. You have to take R2 is equal to R0 reference impedance. Now discussion starts. So this connection, this one and this connection is done for deriving the S parameters. Once if you derive these S parameters, then you can connect anything here, then you can connect anything here practically, then that S matrix is valid for this two-port network. That is the discussion, students. While solving the derivation, we do this type of connection, but once if you get the S matrix, then you remove them, you can connect any load, you can connect any source, that S matrix will be valid. It is similar to the Z parameters, etc., etc. in the network theory. It is similar, right? Now, I am writing the equivalent diagram. Equivalent diagram in network theory. I am assuming you know that. So, this is R0 here, and this one is VG1, okay, and this is port 1. I1 current is there here, and V1 voltage is there here, and now I can transform this impedance R0 here into the equivalent terms for n is to 1. Now this becomes n square into R0 impedance, that is nothing but Z1 now. You know how it is Z1? Actually this equivalent impedance, load impedance R0 for n is to 1 transformer, I can write this at input side. This you will study in network theory, and n square into R0, so Z1. Okay. Now this is the input impedance. Now Z1 is equal to this. Z1 is equal to voltage across this divided by current into this. So that is the Z1 is equal to this one. You got this one. Now students, this V1 V1 you find in terms of VG1. Okay, V1 is equal to voltage across this is equal to VG1 multiplied with this impedance, that is N square R naught divided by this impedance plus this impedance, that is N square R naught plus R naught. You got this one. So from this I will write VG1 is equal to this one, student, R naught gone. So VG1 is equal to N square plus 1 by N square into V1. You got, student. Let us say this is equation number 1. Now I told you the S parameters. So S11, once again I am writing here that matrix B11 is equal to S11 A1, S12 A2. So B2 is equal to S22 A1 plus S21 A2. Right? What the print miss is there. So this is S21 and S22. Right. Now S11 is nothing but B1 by A1, provided if A2 is equal to 0, and I told this one is nothing but Z1 minus R01 divided by Z1 plus R01. Now what is Z1 here? Z1 is nothing but N square R naught. R01, already R01 is R naught. Here we have connected R1 is equal to of course R01 only, that is R01 is given as R naught actually. So that is R naught divided by, have you seen while telling this definition I have connected here R1 terminating impedance R1 is equal to R01, but R01 is given as R naught here. So R naught divided by N square R naught plus R01 is nothing but R naught. R naught cancel. So N square minus 1 by N square plus 1 you got. From this you understood one thing. R naught may be any value. For example, 1 ohm, 10 ohm, 20 ohm. R naught cancel. That means this answer is independent of that R naught. So last year in GATE exam, it seems this is given in 2 marks question for EC students. Their reference impedance, some impedance is given 10 ohms or 1 ohms, not exactly known. So I did not remember. So doesn't matter, students. Here R naught cancelled means this answer is independent of R naught. That actually while doing derivations, no, you have to observe the things. So this is the answer for any reference impedance. Sometimes you can take 1 ohm also, 10 ohm also, like that. Next, here S21 is equal to B2 by A1 if A2 0. I told you that is 2 times of V2 divided by VG1 root R1 by R2, dear students. Now you substitute the things. 2 times V2 divided by, what is VG1, student, here? Here from my equation 1. VG1 is equal to N square plus 1 divided by N square V1. Next, R1 is taken as R naught reference impedance. R2 is also taken as, actually here this is R2. R2 is equal to R02. That R02 is equal to R naught is taken. So this is R naught. Now you know that. So S21 is equal to this cancel, and ultimately you get 2 times N square, numerator, na, N square plus 1 and V2 by V1, N square plus 1. So I will call this as equation number 2. You know that for a transformer, V2 by V1 ratio is N2, number of turns of output side divided by number of turns of input. Now that is given as n2 is 1 here and n1 is n. So v2 by v1 is 1 by n ratio here. So say 3. Put 3 in equation 3 in 2. So that implies you get S21 is equal to 2 times of n square, 2 times of n square divided by n square plus 1 into v2 by v1 is 1 by n. So that is equal to cancellation 2n by n square plus 1. So this is a 4. Now similarly, for the calculation purpose, you take the same diagram. Okay, I am taking the same diagram, and so this is port 1, I1 V1, and this is port 2. Actually, what is the meaning of port, student? There two wires are available, so that you can connect some device there. That is the meaning of port. PORT port means there two wires are available, open wires are available. They are waiting for something to be connected. ये है वो वेट करता रहता है, हम है इधर दो पोर्ट्स, दो वायर्स, कोई आके इधर कनेक्ट कर लो करके बोलते रहता है, वही है पोर्ट 1 मतलब. So this is port 1, port 2, ये वाला I2, this is what do you say, V2. This is the given diagram n:1, right? That given diagram is this one. Now to measure these parameters S12 and S22, you have to make A10. A10 means at port 1 side there should not be any connection, there should not be any source. Then port 2 side source is connected. So let us connect here some source called VG2, generator voltage at port 2, that will have some impedance. You adjust that impedance in such a way that R2 terminating impedance at port 2 becomes R02. That R02 is given as a R0 here, students, R0. Now here some load voltage, load impedance should be there. That is called as R1, terminating impedance at port 1. That is adjusted to R01 value. That R01 is given as R0. So connect here R0, students, this one. Now this is the diagram for measuring other two S parameters S12 and S22. Now draw the equivalent diagram of this one like this. So this is I2, this is V2. Now this is actually R0, okay, VG2. Now here if you transform this to here, ultimately you get impedance here R0 divided by n square. There R0 into n square you get multiplication. Here R0 by n square you get this is nothing but Z2, dear students, because V2 divided by I2, that is. So here Z2 is R0 by n square. So if you write V2 in terms of VG2, so V2 is equal to VG2 network theory, student. Voltage V2 across this impedance is equal to voltage voltage multiplied with this impedance. So that is R0 by n square. Then this plus this. So R0 by n square plus R0. Okay, this is V2. So that is equal to anything cancelled here, something cancels. So that means V2 is equal to, you simplify that one, VG2 n square, R0 by n square, pull out, cancel. Then R0 by n square, here also n square you take. So 1 by 1 plus n square you get, students, right now. So n square, so 1 plus n square, the denominator n square cancel. So this is fine. Now from this Vg2 is equal to V2 into 1 plus n square. So let us say this is equation number 5. Now you write the definitions of S12. So S12 is nothing but B1 by A2 if A1 is equal to 0. So what was this? I told you, if you remember this one, it is similar to that 2 times V1. So 2 times V1 and Vg2 root of R2 divided by R1. So if you substitute in this 2 times V1, Vg2 is nothing but V2 into 1 plus n square and root of R0 by R0, and that is equal to 2 by 1 plus n square and V1 by V2. So S12 is equal to 2 by 1 plus n square, or I will do one thing. So what is the name of this equation? 6. You substitute, put that ratio was there na here. Equation 3. Put 3 in 6. Then S12 is equal to 2 by 1 plus n square, and this is V1 by V2 is required. So V1 by V2 is equal to n actually, right, from that equation. So that implies S12 is equal to 2 times n divided by 1 plus n square. This is 7. S22 is equal to, directly I am writing anyway, right? S22 is equal to B2 by A2 provided A1 0. So that is Z2 minus R02 divided by Z2 plus R02. So here what is Z2, students? R0 by n square minus this is R0 divided by R0 by n square plus R0, right? So now S22 is equal to, so here R0 minus R0 n square divided by R0 plus R0 n square. So denominator n square cancel. So from this S22 is equal to R0 also out, 1 minus n square, 1 plus n square. So equation number 8, students. So after this S11, S12, S21, S22. So S11 is n square minus 1 divided by n square plus 1. So what is S12 here? 2 times n by 1 plus n square, otherwise n square plus 1. Okay. Next S21 is there. S21 is equal to 2n by n square plus 1. 2n by 1 plus n square, otherwise n square plus 1. Then S22, 1 minus n square and 1 plus n square. So this one you remember, dear students, because anytime given you can't do the entire derivation. So this is the S matrix of n by 1 ideal transformer. So you can see here S12 is equal to S21. You can see that. So that represents, that is reciprocal. So this is the derivation of that one. So students, let us solve this one. Find the S matrix of two-port network shown. So this is port 1 and this is port 2. Now let us do the connections for this. So it is like this. I am drawing here. So this is the, some impedance is there here. So this is port 1, this is port 2, Port 1 has I1 current and V1 voltage. Okay, this is I2 current and V2 voltage. Like this it is given. Now you take some source called VG1 and the reference impedance of that is given as R1 is equal to R01, that is given as 1 ohm. And similarly here R2 is equal to R02, we have to connect that R02 is given as 1 ohm. Okay. Now what is the V1 by I1? So that here there is no source. For your convenience you can remove this one and this one. So ultimately V1 by I1 is equal to, okay, so V1, you can remove this one and this one. V1 is equal to Vg1. For time being I am removing them, like this comes, because I2 is nothing, okay, anyway you remove them because I want V1. So V1 means voltage here, voltage here means across these two. So now the parallel combination becomes Z into 1 divided by Z plus 1, and so that here voltage V1 is equal to Vg1 multiplied with this impedance, that is Z into 1 by Z plus 1 parallel combination. So Z plus 1 divided by this impedance plus that impedance, so Z by Z plus 1 plus 1. So that implies V1 is equal to Vg1, and ultimately here you common this one, so denominator Z plus 1, here also denominator Z plus 1. So ultimately after cancellation you get Z by Z plus 1, that means 2Z plus 1. Okay. So from this Vg1 is equal to, what do you say, 2Z plus 1 by Z into V1. Let us say this is equation number 1. Right. Now what is Z1? Z1 definition is V1 by I1, that is equal to V1 by I1 is nothing but impedance seen here. So that is Z divided by Z plus 1, dear students. Right? Voltage across this divided by current into them, their parallel combination Z by Z plus 1. Now of course if this is what do you say, V2, and then V2 is equal to V1, so V2 by V1 is actually same, V2 is equal to V1 here. Now let us write the parameter S11. S11 is equal to Z1 minus R01 divided by Z1 plus R01, ZL minus Z0 by ZL plus Z0. So Z1 is actually Z divided by Z plus 1 minus R01 is 1 ohm divided by Z plus 1 plus 1. Ultimately denominator same, so Z minus of Z plus 1 divided by Z plus 1, that is equal to Z minus Z gone, so minus 1 by 2Z plus 1 you get, S11. Okay. Next next definition is S21. S21 definition directly I am writing, students, I am not writing anything here. So that is 2 times V2 divided by Vg1 root of R1 by R2. So here I was telling you that R1 is equal to R01, that is taken as a 1 ohm, and here R2 is equal to R02, that is taken as 1 ohm here, that is given in the question. So ultimately this is 2 times V2. What is Vg1? gave the equation number. So let us say this is equation number 2. Now let us say this is equation number 3. So you put equation 1 in 3. S21 is equal to 2 times V2. Vg1 is 2z plus 1 divided by z. So V1 root of R1 is 1 by 1 actually, that is equal to 2 times z divided by 2z plus 1 and V2 by V1. So students, here V2 by V1 is 1 na. So ultimately 2z by 2z plus 1 you get, because here V2 is equal to V1. So V2 is equal to V1. Okay. So this V2 by V1 is, if you want you can put this as equation 1 dash. Okay. So this is, let us say, equation 4. Put equation 1 dash in 4. That implies S21 is equal to 2 times z divided by 2z plus 1 into 1. You know this multiplication, but procedure you have to observe. Procedure. Without skipping anything, I am writing everything neatly so that you will not be confused. Kuch confusion nahi rahega. So in network theory, you know that this is reciprocal network as symmetric. So that is why no need to solve other parameters because given two port network is symmetric. So S11 is equal to S22 and reciprocal. That is why so S12 is equal to S21. So now S matrix S11, S12, S21, S22 is equal to S11 is what, students? Minus 1 by 2 times Z plus 1, and S12 anyway S21 we have solved, that is 2 times Z divided by 2 times Z plus 1, and this is also 2 times Z by 2 times Z plus 1 minus 1 by 2Z plus 1. So this is the matrix. It is better you remember this one instead of solving this one. This is you remember like a standard question. Okay. So students, let us solve this question. Find the S matrix of a transmission line. The length of that is L, is shown below. Given R01 is equal to R02 is equal to Z0. What is Z0? Characteristic impedance of the transmission line. Now you take this transmission line of length L, given characteristic impedance is Z0, dear students. This is port 1, this is port 2. Now let us do connections for finding the S parameters. Actually this R1 is equal to R01, that is given as Z0. So that means that is Z0. So simply this is Z0, student, Z0. So here Vg1 is there plus minus Vg1. Okay. Now into the let us finish this also. Here port 2 it is. Here some load impedance is connected. That is nothing but R2. So that R2 is equal to R02. That is given as Z0 here, characteristic impedance. That means load impedance to this one. I am putting this in box because that is the explanation that why we are connecting Z0 here. It is given Z0. Here it is given Z0. This is actually I1 and here this is V1, voltage V1. Okay. Now we have to see the property of the transmission line. Already we know that in a transmission line, whatever might be the length, whenever you connect ZL is equal to Z0, then transmission line impedance at any distance is Z0. We have solved that one. If you want that we have seen Z of D is equal to, what do you say, Z0 ZL plus Z0 tan gamma D divided by Z0 plus ZL tan gamma D. So Z at any distance, if ZL is equal to Z0 implies it is matched at load. So that means we get Z0. So in place of ZL we put Z0, no students. So Z0 tan gamma D divided by Z0 plus Z0 tan gamma D. So already we have done it, this I have written this cancel, ultimately you get Z0. So if load is connected with characteristic impedance, so this is matched, and also here nothing is reflected, students. That's what we want to calculate S11 and S21 parameters. We have to make reflected signal 0. So by connecting Z0 here, reflected signal is made 0. So A2 is made 0 here. That is the requirement to calculate S11 and S21, students. So the conclusion is impedance of the transmission line at any distance is Z0. That means Zin also is equal to Z0. So that means the Z1 is nothing but V1 by A1. Input impedance of this transmission line is Z0 only now. So that means Zn is equal to Z0. So Z1 that is nothing but V1 by I1. That is nothing but Zin. So that is equal to Z0 here. Okay. Now, dear students, here what is V2, students? Actually V2 is equal to whatever voltage is there here, V1 e power minus of gamma L, because total voltage here is equal to, at load is equal to incident voltage plus reflected voltage, but matching is done, so reflected voltage is 0, only incident wave is present. So that is for wave traveling in plus Z direction, minus should be there, and Z is equal to total length you have substituted. So V2 is equal to V1 whatever you are sending multiplied with e power minus gamma L, because no reflected wave, only incident wave is there. So load is matched, because load is matched. So there is no reflected wave. So there is no reflected wave, student. No reflected wave. Now let us write the parameters. S11 is equal to Z1 minus R01 divided by Z1 plus R01. So Z1 I wrote here, Z1 is equal to Z0 only, minus R01 is Z0 only, divided by Z0 plus Z0, that is 0. There is no reflected wave at port 1 because it is matched here. Nothing, no reflected wave. That is correct. Theory also says same thing. Maths also saying same thing. So reflection coefficient at port 1 0, because the input impedance is Z0. The load impedance is also Z0. Z0 matched here. So input side reflection coefficient is Zn minus Z0 by Zn plus Z0. Zn is equal to Z0. Z0 minus Z0 by Z0 plus Z0, 0. So there is no reflected at port 1. Now coming to the that parameter S21. That is nothing but 2V1 divided by VG1 root of R1 by R2. So here somewhere I have calculated that VG1. Okay. If input impedance is, dear students, input impedance is Z0 na. So input impedance is Z0 na. So V1 is equal to VG1 and impedance here, input impedance I will write here, input impedance is equal to Z0. V1 is voltage at input impedance. So here voltage is equal to, that means V1 is equal to network theory. Here Z0 is the impedance. So here voltage is equal to V1 is equal to VG1 into impedance here, that is Z0. I will write one more step so that you will not be confused. Zin, because this V1 is voltage across Zin divided by Zin plus this Zs, Z0, that is. So VG1, no, this is. So VG1 and Zin is Z0 divided by Z0 plus Z0. So ultimately this is VG1 by 2. So let us call that is some equation. We call this as equation 1. Okay. So call this as equation 2. Put 1 into Z21 is equal to 2V1 divided by, what is VG1, student, from that? VG1 is equal to 2 times V1, na? 2 times V1. 1 minute, students. So here there is a print miss, student. थोड़ा गड़बड़ है इधर. V2 लिखना है ना, ये 2V2, right, 2V2. So 2V2. Next VG1 is nothing but from this VG1 divided by 2 is equal to V1. So VG1 is equal to 2V1. So you get 2V1. अब सही है, 2V1. VG1 is equal to 2V1. Now R1 is Z0. This is Z0. That is equal to 2 cancel. So V2 by V1. Let us say this is equation number 3. One more equation is there here. We have written. Let us say this is equation number 1 dash. So put equation 1 dash in equation 3. So that means S21 is equal to from equation 1 dash V2 is equal to V1 e power minus gamma L divided by V1. So that means ultimately you got e power minus gamma L, students. So actually what is the meaning of S21 theory statement wise transmission coefficient from port 1 to port 2. So while transmitting it experiences e power minus gamma L term. So that's what you got. So this transmission line also reciprocal and symmetric. So no need to calculate other parameters. So this is a TX line, because you may take that side as input 1, this side as input 1, no problem. Then whatever transmitted from that side to this side or this side to that side, it will be same. So transmission line is symmetric. So S11 is equal to S22 and reciprocal. So S12 is equal to S21. Now ultimately the matrix becomes S matrix S11, S12, S21, S22. It becomes here S11 is 0, so this is also 0, and S12 is e power minus gamma L. This is also e power minus gamma L, students. Okay, this is the answer. It is better you remember this one for what do you say, transmission line. But if it is a lossless transmission line, then gamma becomes for lossless transmission line, gamma is equal to j beta. So S11, S12, S21, S22 becomes 0 e power minus j beta L, then e power minus j beta L 0 you get. Then what is the mod of this? 1. Mod of this is also 1. That means lossless we are saying, na? For lossless, definitely modulus of S1, S12 and S21 should be 1. And also reciprocal, and modulus of this is 1. In the note I have written, modulus of S12 is equal to modulus of S21. Here you can find modulus of S12 is equal to e power minus j beta L. And what is the modulus of this? So root of cos square beta L plus sin square beta L, that is equal to 1. Similarly, what do you say? Modulus of S21 is also 1. I already told you, yes, modulus of S12, modulus of S21 is equal to 1. Then that is lossless. Already it is lossless network. Okay. So dear students, waveguides. What is waveguide? It is single conductor. It is in the pipe form, PIPE, pipe. Hollow pipe. Hollow means inside empty. So waveguides, waveguide is a metallic. Metallic means conductor, student. How many conductors? Single conductor. Metallic pipe. Pipe means inside hollow. Hollow metallic pipe. Waveguide is a metallic pipe. So that is hollow metallic pipe actually. So waveguide is a metallic pipe of rectangular or circular in cross section. Cross section means the front view. So rectangular waveguide means like this. It is for example, you are inside a room and remove the front wall of this room, back wall of this room, then only 4 walls are there. These 4 walls are made up of conductors. Then inside your room, air medium is there. Then all the 4 walls are perfect conductors. That is called as a rectangular waveguide. Now this is open, and this side also open, and these 4 walls are actually conductor walls. This is called rectangular waveguide, RWG, rectangular waveguide, student. RWG, rectangular waveguide. Now that means here you take this, assume this is a perfect conductor. It is not a wood, lakdi nahi hai. Perfect conductor you take. Then drill a hole here. You do the drill a hole. This black region ना, काला वाला है ना, वो ड्रिल करके निकाल दो उसको, इस साइड से लेकर इस साइड तक निकाल दीजिए. निकालना है. निकालने के बाद खाली हो जाएगा अंदर. वो खाली जगह में एयर को भर देंगे. Then it is called air filled rectangular waveguide. Then you can fill up some other dielectric material, that is called dielectric filled rectangular waveguide. Okay, students. So now, what is a rectangular waveguide? It is a hollow. Hollow means inside empty. Hollow metallic pipe of rectangular cross section, and for this end is also open. That end is also open. You will be sending EM wave here. EM wave will be coming out there. Now you take a conductor like this, conductor sheet. What is this? Conductor sheet. It is not a paper. Assume that it is a conductor. It is not a paper, it is a conductor. Then you roll this sheet like this. Which sheet? Which material sheet? Conductor material sheet. Like this you roll. Now what is the shape of this? Cross section means front view. It is a circle. What is this material? Conductor material. How many conductors are there? Single conductor is there. Now this is called circular waveguide. So circular waveguide is a single conductor in the form of cylindrical shape, and this end is also open and this end is also open, and here you will send the input signal, here you will come the output signal. That is called CWG, circular waveguide. Circular waveguide. So that is also single conductor, circular waveguide. Okay, so this is all conducting surface, and like this is a conductor surface, and this is a open, here also open. This is input, that is output is sent there. So conductor surface, and this is called a circular waveguide, or otherwise it is also called a cylindrical waveguide. CWG, circular waveguide, or otherwise cylindrical waveguide. Okay, so circular waveguide. Actually it is a cylinder, but the front end is circle shape. So that is why cylindrical waveguide, or otherwise circular waveguide you can call CWG. How many conductors are there? Single conductors. In this, how many conductors are there? Answer, single conductor. But students confuse. I told you in your room, you remove the front wall. आपका कमरे में फ्रंट वॉल को निकाल दो और पीछे वॉल को भी निकाल दो और बचेगा 4 वॉल्स बचेगा. So there are 4 walls remaining if you remove the front and back wall. Then how many walls are there? 4. This side one, top one, bottom one. How many walls are there? 4 walls are there. What is the material used? Perfect conductor. Then that is called rectangular waveguide. So there are 4 conducting walls, but there is a joining there, and that is why after joining you will have single conductor only. 4 walls are there, but joining is there. Every wall is joined to each other, so that single conductor is there. So 4 conducting walls are there, but single conductor. Okay, right, students. Now what is the difference between two-wire transmission line and the waveguides? In two-wire transmission line, there are 2 conductors, first conductor and second conductor. 2 conductor structure it is. Coaxial cable, central conductor is there, and also here coaxial cable, central conductor is there here, this one, and outer conductor is there, this one. This is also conductor, outer conductor is there. So how many conductors are there here? 2 conductor. For example, planar line. I told you planar line. I told you planar line means you take a dielectric wood material here like this. Wood material you take. So ये लकड़ी है, ये dielectric है, ये dielectric है, dielectric है, ये dielectric. And top side you put one conductor sheet of some thickness, top side, and similarly bottom side also you put some conductor sheet, that is called a planar line. Okay, this is also top conductor, bottom conductor, 2 conductors are there, and these are all 2 conductor structures. They are actually 2 conductor structures they are, but these are single conducting structures. 4 conductor walls are there and they are joined here. So once again I am showing you, for example, Some students may confuse, that is why. So this is one conductor surface and like this, and this is second conductor surface like this, and these two conductor surfaces are joined here. Joining is done. After joining is done, that is called total single conductor. So that is conductor surface 1, and this is conductor surface 2, and here one more surface is taken, and bottom side one more surface is taken here. So all the conductor surfaces are joined here like this, so that there are 4 conductor walls, and they are joined here, so that total number of conductors 1 and number of walls 4. Now dear students, here one wall is there, here bottom side also one wall is there. Now inside this, if air is there, that is called air filled rectangular waveguide. If dielectric is filled, that is called dielectric filled rectangular waveguide. Now this is one wall, this is one wall. Here this wall is also closed. This wall is also closed. That is called cavity. CAVITY, cavity, rectangular cavity, that is called. So that rectangular cavity is used to store microwave energy. Like in network theory, LC resonant circuit is there, and that is used to store the energy at resonant frequency. Similarly, this cavity is also used to store the energy at resonant frequency. So students, uniform plane wave chapter we have studied already. Here EM wave is radiated into the air, then it can go in any direction. It can go up to any distance. So that is why uniform plane wave is unbounded and unguided. So it is actually, uniform plane wave is it is unguided. Unguided means in a waveguide, signal has to be transferred from one end to other end along the axis of the waveguide. But here that is guided. I will write that also. So waveguide is guided. It guides the wave in the direction of wave axis. But here it is unguided. So EM wave can go unguided. So here EM wave can travel, EM wave can travel in any direction. It can travel in any direction. Okay. So it is unbounded. Unbounded. That means if EM wave is going like this, nobody stops that one. If it has energy, it can go to up to infinity distance. But here in a waveguide, it is not like that. EM wave is traveling, then whenever conductor wall comes, it has to be reflected back. That means that is bounded by the conductor wall. Bounded means stopped. Bounded means stopped. It is unbounded. That means EM wave student, here EM wave. So here EM wave can travel up to infinity distance if it has energy. If energy is there, because of energy, it may stop going, but otherwise nobody stops that one. Okay, that is the meaning. अगर उसके पास एनर्जी खत्म हो गया तो वो रुक जाता है, बट लेकिन उसको कोई स्टॉप नहीं करेगा उसको. So that is unbounded. So EM wave can travel up to infinite distance if it has energy. So nobody stops that one. But whereas this one, wave guide, no student, it is different. So wave guide, actually guide means रास्ता दिखाने वाला है. Guide shows the path to the wave. So this wave guide actually shows path to the wave, EM wave. सो ये वेव गाइड है, रास्ता दिखाता है वेव को। वो वेव गाइड बोलता है वेव को, आप आइए इनपुट में एंटर हो जाओ, और एंटर होके मेरा को वेव गाइड एक्सिस है, उस एक्सिस का डायरेक्शन में जाइए करके बोलता है ये, इसलिए उसको वेव गाइड बोलता है। सो इन दिस EM wave is guided, actually guided. That means EM wave travel from one end to other end along the axis of the wave guide. Dear students, what is the definition of axis of the waveguide? The center line of the waveguide is called axis of the waveguide. Okay, it is guided, and also it is bounded here. It is bounded. That means EM wave is reflected, or otherwise EM wave is stopped. EM wave is stopped. EM wave is reflected or bounded. EM wave is reflected or otherwise bounded by conductor. Perfect conductor, students. The conductor means here by conductor walls. We will discuss that also. It is bounded. That means stopped. So, if you see I am writing here fourth point. I told you in a waveguide, EM wave travels in the direction of waveguide axis through multiple reflections. So, dear students, here I am showing you this waveguide like this, a rectangular waveguide. So, this is actually conductor walls. This is the input, and this end is output. Now, for example, if signal enters like this, and that is the EM wave, then here conductor surface came, it reflects that, reflected like this, again reflected like this, again reflected like this, so again reflected like this, it keep going, students. Okay, and ultimately it enters the output like this. So input EM wave, this is output EM wave, it comes out. Now if you see carefully, this is input EM wave and this is output EM wave, so it is coming out. So dear students, what is happening here? This is top conductor wall, bottom conductor wall. Here medium is there. Here medium is there. In here medium. That means this signal or otherwise EM wave is traveling in this medium and going from one end to other end along the waveguide axis. That means in the direction of waveguide axis through multiple reflections at the conductor walls. If you want, I will show you here like this. It is you can see. So this is the waveguide. Okay, this one, this is the waveguide. So this is one conductor wall, this one, and this is also one conductor wall, this is also one conductor wall, this is also one conductor wall. How many conductor walls? 4 are there. There are 4 conductor walls, but how many conductors are there? One conductor, because here joining is done, here also joining is done, here joining is done. That is why one conductor, single conductor it is. So now students, this is input end, this is output end. If air is filled here, this is air filled rectangular waveguide. The material of this is perfect conductor, all are perfect conductors. Now EM wave enters here, it goes here. This is called, center line is called axis of the waveguide. But actually the width of this is centimeter, the height of this also centimeter, that is very small actually. Here to maintain the smooth surfaces, perfect conductor surface is taken, gold coated here, with gold coating is done, because gold is non-reactive, so that if it is not reacting lifelong, that surface is maintained very smooth, so that much dispersions will not occur. Anyway, nobody will ask you all those things. So dear students, now this is centimeters, few centimeters, this is also few centimeters. Now always EM waves, no, they enter the waveguide at some angle like this. Here, no, they enter at some angle like this. Now when a EM wave enters here like this, it hits this conductor wall. Then here it is perfect conductor. Reflection coefficient here is 1. So whatever EM wave hits here, it is entering like this and hitting here. Then completely it is reflected like this, and it is reflected again, hits here. Again, this is also perfect conductor. Reflection coefficient is 1. Magnitude of reflection coefficient. Again, it comes out. It goes out like this. So if any EM wave hits coming like this, then again it is reflected and it comes out. Ultimately, final direction is waveguide axis direction, dear students. That's what I am telling. But if EM wave enters here and it is hitting here, it reflected back, again hits here, and again it goes out. But where it is traveling in this medium present inside the waveguide. So you should understand there are two things here. One is waveguide is traveling in this medium, and that is stopped by this boundary, and here reflections occurring. So many reflections means multiple reflections. Now statement, you listen carefully. In the waveguide, EM wave travels in the medium. This is the medium. It is traveling in the medium present between the conductor walls along the axis of the waveguide through the multiple reflections. That is the statement. So now if you see here, this impedance of this one is eta 1. The impedance of this conductor is here, top side conductor is there here, like this conductor surface is there. So this is conductor, this one conductor surface, the impedance of that eta 2, let us say. Now if eta 1 is what do you say, lossless dielectric, na? Generally we fill air medium, or otherwise lossless dielectric we fill up. So here eta 1 is root mu 1 by epsilon 1. That is because we take lossless dielectric medium. Lossless dielectric medium, because sigma is 0 for that. Now eta 2 is for conductor. Eta 2 is equal to j omega mu divided by sigma plus j omega epsilon, but that is medium 2 conductor. Conductor surface is we are taking as medium 2. Inside that there is a medium, dielectric medium, that is medium 1, and for medium 2 suffix 2 is taken like this. So if it is for perfect conductor, if conductor wall is perfect conductor, so sigma 2 is equal to infinity, implies if this is infinity, students, eta 2 becomes 0. Now ultimately gamma is eta 2 minus eta 1, eta 2 plus eta 1, that is equal to minus 1, because 0 minus eta 1, 0 plus eta 1 minus 1. That means whatever transmission coefficient is what, student, now? So that implies transmission coefficient is equal to 1 minus 1, 0, because gamma is minus 1. That means whenever EM wave hits the conductor surface, nothing enters into the conductor. I have shown you, no, like this. When EM wave hits the conductor like this, this is eta 1, this has eta 2, hits the conductor surface like this, completely reflected. That is what we want actually. No signal enters into this conductor wall, By chance, if any signal enters into the conductor wall that is dissipated in the form of heat, then no use of that. In the waveguide, we are making the signal to travel in this medium. So whatever signal is traveling in this medium, that only goes out. By chance, any signal enters into the conductor walls that is dissipated in the form of heat, they are called conductor wall losses. Conductor wall losses. So in this case, there are no conductor wall losses, dear students. Yes or no? I am writing the statement. In the wave guide EM wave, or that is also called signal, high frequency signal. EM wave means high frequency signal. Travels in the medium, travels in the dielectric medium present between conductor walls. That is one statement. So where signal travels in the dielectric medium, here medium is there, no, that medium. In the waveguide, EM wave travels in the dielectric medium present between the conductor walls. That is one statement. Next, in which direction signal goes along the waveguide axis? How? Through multiple reflections. So EM wave travels in the direction of waveguide axis through multiple reflections at conductor walls. Okay, EM wave travels in the direction of waveguide axis through multiple reflections at conductor walls and leaves other end. That means it will go out of the second end here. So EM wave travels in the direction of waveguide axis through multiple reflections at conductor walls. These reflections occur at conductor walls and leaves other end. If conductor walls are made up of perfect conductor, then reflection coefficient at conductor walls is -1 and no signal, that means EM wave, no signal enters into the conductor walls. No signal enters into the conductor walls. So there are no conductor wall losses. If we use very good conductor, then sigma is very high but not infinity. So gamma is slightly less than 1 and transmission coefficient is not 0 but very less. Example, if gamma is equal to minus 0.99, then transmission coefficient is 1 plus gamma 1 minus 0.99. So transmission coefficient is 0.01 student. That means very small. So if we use very good conductor, this story is written. In this case, very small, very small amount of EM wave or otherwise EM power enters into the conductor wall and dissipated in the form of heat. These are called conductor wall losses. But they can be neglected because that transmission coefficient is very less, and why we can neglect that? Because waveguides we use for a very small distance, for meters of distance, not kilometers. That is why that loss is present, but length of the waveguide is very small. We use, for example, in satellite communication engineering, this is the room where you make the satellite signal. Then inside this room, to top up the roof antenna is there. We use rectangular waveguide for very small length. So that is why those losses can be neglected, dear students. Right. Anyway, now I told you inside the waveguide. So this is conductor wall. Inside the waveguide, now we spoke of reflections. That story is over. Now here EM wave is traveling in this medium. Now what we do? We select perfect dielectric. For perfect dielectric, sigma is 0. If sigma is 0, then alpha of this medium is 0. Then there are no losses. That is the story. But we can never get perfect dielectric. We can select best dielectric. Already I told you, for best dielectric, sigma of the medium is 10 power minus 17. Then because of that, alpha value is present. And if alpha is present, then dielectric medium losses are also present, but that alpha value is very less. So we can neglect that one also. So if the medium between the conductor walls is perfect dielectric, then perfect dielectric, that means sigma of the medium is equal to 0, then alpha 0. So then, or otherwise, then there are no dielectric medium losses. But we are saying perfect dielectric, we can never get perfect dielectric. We can get best dielectric. If the medium between conductor walls is best dielectric, then sigma is approximately 10 power minus 17. It is not 0 but very less. Okay. Then alpha is not 0, then alpha not 0 but very less. That is also because if sigma is very less, alpha is also very less. This you have seen in the uniform plane wave chapter. Already we have discussed this in uniform plane wave chapter. So if the medium between conductor walls is best dielectric, then sigma m is not 0 but very less. Alpha also not 0 but very less. There are dielectric medium losses which can be neglected. I told you why we can neglect. So very small dielectric losses are there, very small conductor losses are there, but we can neglect them because we are not going to use the waveguide for longer distances, kilometers we will not use. Where we use waveguides in gigahertz frequencies. For example, satellite signals, you will be studying that satellite communication. Satellite signals, we will use gigahertz frequencies. So where you not manufacturing student, where you generate the satellite signal from the satellite room to the you have to send a satellite signal is generated in the inside the satellite station. So there inside the room microwave generators are there, then signal is modulated there, then you have to send to the transmitting antenna which is present on the roof of the building. So it may be 100 meters, 200 meters long, maybe 500 meters long, not more than that, dear students. So that is why you can neglect them. Okay. So dear students, let us see the difference between two conductor transmission structures and single conducting transmission structures. So two conductor transmission structures and single conductor transmission structures. First point, like two-wire transmission line is one example having two conductors, and coaxial cable is also example. Center conductor is there here and this is outer conductor. So in the coaxial cable, this is center conductor, this is outer conductor. Two conductors are there. Here I told you voltage source is connected. Like this. If you want, I will show you here. like this it is connected, and current goes like this, supply to the load ZL, and again comes back, current comes back in this conductor I. Similarly here also you connect to this voltage here, grounded, then current goes here in the inner conductor I, then it goes travels here, then here load is there ZL, and that I current goes out in this, like this, in the outer conductor. Okay, I current goes like this, it comes back again. So 2-wire transmission line, coaxial cable, planar transmission line, these are all 2 conductor structures. Now let us talk of single conductor transmission structures. Rectangular waveguide, rectangular waveguide, so that one, and circular waveguide, this one, single conductor. Okay, these are the 2 conductor transmission structures. These are the single conductor transmission structures. This is point number 1. So here point number 2 I will write here. So I already told you, student, they are that means these two conductor structures, they are low pass filters. I told you, no, if you draw I am telling you here, see students, for example, you take a lossless transmission line, students. You are taking lossless transmission line, okay? Now V1 is equal to 10 volts you are sending here, input side. Then output side, how much you will receive, students, if it is lossless? Definitely 10 volts only. Then what is the gain of this? Gain is equal to output voltage by input voltage, that is 10 by 10 is equal to 1. Transmission structure is not an amplifier. It is not an amplifier. Simply transfer signal without loss. Then gain is always 1. Then at the DC frequency, if I send 10 volts, here also 10 volts is received. So let us take gain here, gain, and versus frequency. But DC voltage, if I send, total voltage is received. So gain is how much? 1. Now I am doing testing. Now sinusoidal signal V1 is equal to 10 sine 2 pi ft. Frequency keep increasing, frequency increase here gradually. Then up to some megahertz frequency, same output is received. So that gain is 1. But if the input frequency is very, very high, more than hundreds of megahertz, then EM wave starts radiation here. That EM wave, whatever you connect here, otherwise high frequency voltage, whatever you connect here, the total signal cannot receive here because radiation is there here. That means output voltage reduces. That means gain reduces here. After some frequency, gain starts reducing. And if you increase the frequency is very high, then nothing goes here. Then gain becomes 0. That means what is happening here? Why gain has become now it is this has a cutoff frequency here, FC. Yes or no? Of course, you call in filters FCH, and cutoff frequency is there. Why here gain is not there? Otherwise, why signal is not received? Because of radiation losses. Because of radiation losses. That means it is a low pass filter. Then what is the lower cutoff frequency for this? There is no lower cutoff frequency. What is the meaning of lower cutoff frequency? From which frequency it can start sending the signal? From 0 frequency. From 0 hertz onwards, that means DC signal also it can transfer these 2 conductors. So that is why there is no lower cutoff frequency for this one. That is also objective question, student. For which of the following transmission structures there is no lower cutoff frequency? Answer: two conductor transmission structures. So I will write this here. So they are low pass filters, LPF. Now here if I draw the gain versus frequency, then the plot is like this. Gain is 1 at low frequency onwards, then gradually it becomes what do you say, 0. This is called cutoff frequency FH. Okay, now is it flat? Because I am very tall, no? So okay, like this it is coming. So dear students, here why there is no signal transmission here? Radiation losses are there. What are there? If F greater than FH, then radiation losses are present, dear students. Right? Conductors start radiating. That means conductor start radiating means high frequency cannot travel through this conductor. Now that is why those researchers intelligently thought that if very high frequency, then we will send the signal in the medium present between the conductors. So that is the logic in transferring from two conductor structure to one conductor structure. So here at high frequency, once again I am writing at high frequency, two conductor structures have radiation losses. Next one, they do not have lower cutoff frequency. They do not have lower cutoff frequency. Meaning is they can transmit signal. They can transmit signal from 0 Hz onwards. Because some students confuse, that is why I am writing very clearly. Some students confuse, they don't have lower cutoff frequency. What is the meaning? They can transmit signal from 0 Hz onwards. So that is the meaning of that one, student. Now here coming to this one, they behave like high pass filters. High pass filters. Okay. Here if I draw like this, gain and versus frequency, and we are going to derive this. Don't worry about this. Here it will have a cutoff frequency FC. Then onwards it will have some gain, constant gain it maintain. That is gain is 1 here. So here we are going to derive. ये आपको अभी समझ में नहीं आएगा, डिस्कस करने वाला है. We are going to discuss. So if F less than cutoff frequency, then alpha not 0, student. Alpha not 0. So beta is equal to 0 we will get. So if alpha is 0 means there is an attenuation. Attenuation is present here. That is why low frequency signal cannot be transmitted in the single conductor structure, because attenuation constant is present. Attenuation is present. But here if F greater than Fc, here F, if no need to write, so F greater than Fc, here we will derive that alpha 0 and beta not equal to 0. Here there is a transmission here and there is no attenuation, student. So it has cutoff frequency, lower cutoff frequency. The meaning is it has lower cutoff frequency means it cannot send signal from 0 Hz onwards. If the, for example, FC is equal to 1 gigahertz, we got. We are going to discuss that. Don't worry. We are going to discuss. If FC is equal to 1 gigahertz, the meaning is then this waveguide can transmit the signal more than 1 gigahertz, but it cannot carry the signal from 0 Hz onwards. So that is why they have lower cutoff frequency, students. So here I will write two lines. If F less than Fc, then due to attenuation, signal cannot be transmitted. Okay, next point. They have lower cutoff frequency. That means the meaning is that is if F greater than Fc, then only signal is transmitted. Then only signal is transmitted. That is the meaning. Right? Now third point, student. Third point है. So two conductor transmission structure and single conductor transmission structure. So third point is that here EM wave is transmitted in TEM mode, transverse electromagnetic mode. Okay. Here EM signal or otherwise EM wave is carried transverse electric TE. We are going to study that also. TE or transverse magnetic or otherwise HM, hybrid mode. That is combination of TE and TM. So hybrid mode. Okay. They cannot carry EM wave in TEM mode. So they cannot carry that rectangular waveguide, circular waveguide. They cannot carry EM wave or otherwise signal in TEM mode. If I want, I will tell you in the heading itself it is there because to carry energy. See, if signal is carried in TEM mode means why are you sending the signal? To transfer energy or otherwise to transfer power. So you say energy or power here is transferred using TEM mode. Now why you can't send energy using the TEM mode here? There are equations. By equations you can observe. By theory wise also you can observe. I will tell you. Common sense. I am telling you TEM mode goes in two conductor structure. That means to have a TEM mode, minimum conductors required 2. But here number of conductors 1. That is why you can't carry. Now I will explain you why you can't, TEM mode is carried in two conductor structure. Anyway, nobody will ask. If you want answer, I am explaining, you see. Right? You take the transmission line. How many conductors are there? 2 conductors. Now, first of all, let us take this as a Z axis. What is the definition of TEM mode? TEM mode means for wave traveling in Z direction, EZ should be 0 and HZ also should be 0. In the uniform plane wave, I wrote this in the box, student. डब्बा में लिखा हुआ था ये, फिर बार बार एक्सप्लेन नहीं करना. For wave traveling in Z direction, in case of TEM mode, EZ should be 0 and HZ should be 0. And also, that is uniform plane wave. Here, electric field direction, magnetic field direction, and power flow direction, they are perpendicular to each other, my dear students. Perpendicular to each other. Okay? Right. Now, you have to answer my question. In cylindrical system, before explaining, I am doing groundwork. वो समझने के पहले कुछ और पढ़ रहा है. So TEM mode means for wave traveling in Z direction, electric field Z component also should not be there, and magnetic field Z component should not be there, because transverse means 90 degrees. Electric field and magnetic field both are 90 degrees to wave propagation direction. That is the meaning, that is the definition. Now, one more point. In cylindrical system, A rho, A pi, A z, how are they? Perpendicular to each other. Now I will start explaining this one. I have taken first conductor, second conductor. How many conductors? 2 conductors. Now I am connecting here some voltage like this. Then here what is going? Current is going. If current, I will remove this. This is the load actually, load ZL. So this is Z direction. I will take this as a Z axis, no? Z axis. Okay. Now current is going in this direction. In which direction? Z direction. This current carries the signal or otherwise energy in which direction? Z direction. So now students, current is in Z direction. So power also carried in Z direction. AP cap means unit vector in power flow direction, that is in Z direction. 1 point over. Next point. If current is in Z direction, according to right hand thumb rule, put the thumb in current direction, then in the circle closed finger direction, magnetic field is there. That means because of this current, magnetic field is like this H bar. So that H bar has some value H naught into A rho cap. No, A pi cap, circular, no? I am using cylindrical system. This is Z direction. This circular is actually pi direction. Next discussion. To have a current in Z direction, you have connected voltage source here. This is actually positive terminal. This side you have negative terminal. So the here plus minus like this you will have. That means electric field direction is from plus to minus electric field. So in cylindrical system, this is Z axis. Now this one is actually pi axis. This one is radial direction, rho direction. So that means E bar is equal to some value is there, E naught into A rho cap is there. Now you tell me, power flow direction is Z direction, but magnetic field is in pi direction, electric field is in rho direction. That means magnetic field Z component is 0 and electric field Z component is 0, and electric field and magnetic field do not have Z components, and also power flow direction is AZ and electric field direction is A rho and magnetic field direction is A pi. They are mutually perpendicular. So conclusion. In this case, that means in transmission line, power is going in Z direction and the electric field and magnetic field are in rho and pi directions respectively. That means they don't have electric field and magnetic field do not have electric field and magnetic field values in z direction. That is why it is a TEM mode. That is the explanation. And also in this electric field, magnetic field and power flow direction, they are mutually perpendicular. In uniform plane wave, they should be mutually perpendicular. So now finally, this two-way transmission structure is carrying the energy from source to load in TEM mode. Then what is going here? Current is going. To have a current minimum, how many conductors are required? 2 conductors. Why like that? One conductor carries the current from source to load. Other conductor carries the current from load to source in return path. That is why minimum 2 conductors are required. So that is the conclusion, students. So to have a TEM mode, minimum 2 conductors required. But in circular waveguide and rectangular waveguide, you have only a single conductor. That is why they cannot carry the energy or otherwise signal in the TEM mode. They carry the energy or otherwise signal in the TE or otherwise TM or otherwise HM. Combination of TE and TM mode is called hybrid mode, called HM mode. Okay. So if signal is going means energy also going, because signal carries energy. Already you study this in the communication system, right, students? Okay. So dear students, now let us discuss propagation constant. Propagation constant in the waveguide, of course, rectangular waveguide, students. First we will discuss rectangular waveguide, then after that we will extend the discussion for circular waveguide. So propagation constant in the waveguide. So that is propagation constant is gamma actually. In uniform plane wave, gamma it is called, but in a waveguide, so it is a guided, so that is why gamma g it is called. Okay, gamma g. Now one by one let us discuss. The propagation constant in an unbounded medium. Unbounded medium means, dear students, that is uniform plane wave only. Unbounded medium means, or otherwise I will tell you like this. Medium means like this, air medium, dielectric medium. Then around this medium there are no conductor surfaces. So if I see this is antenna, if I send signal here, it can go up to infinity. Now this is called unbounded medium. There are no conductor surfaces. The propagation constant in an unbounded medium is gamma, and that gamma is equal to j omega mu into sigma plus j omega epsilon, and already we know that one. If the medium is lossless, that means sigma 0, then sigma 0 you get gamma is equal to j omega root mu epsilon, and gamma square is equal to minus omega square mu epsilon. Let us say this is equation number 1. Okay. Now this is waveguide. We will take this as a x-axis. Okay, x-axis. We will take this as a y-axis. This much not required. This much not required. Okay, we will take this as a y-axis. Now, in the this is called what, students? X is equal to 0 wall, because for this x value is 0, so this is called x is equal to 0 wall. That means this one, no? This one. So I will show like this. X is equal to 0. Which wall? Which wall? Conductor material wall. X is equal to 0, conductor wall this is. And here there is another wall that is actually x is equal to a meters. I am taking here to here. Generally that is in centimeters. So this is called width a. Otherwise this is also called as breadth. That means the larger dimension, that is x is equal to a conductor wall, that is. Now similarly here like this, you say this wall is there and this wall is there. This bottom one is called y is equal to 0 conductor wall, and top one is called as here I am taking height as a b actually. So y is equal to b conductor wall. This is so this is b, this one. So how many conductor walls are there? 4 are there. Now it has a, what do you say, it has some length here. Okay, this much anyway, like this. So we are taking this as a z-axis. Why I came from this discussion to this discussion, you know? I want to tell you, in x direction signal cannot travel because these conductor walls are there. If I send any signal like this, na, it cannot go in x direction because that signal is stopped by this wall. That means in a waveguide, x direction signal is bounded. Bounded means stopped because of conductor walls. Similarly, in the y direction, if I send signal, that is also stopped by the conductor walls. So in the waveguide, rectangular waveguide, in the x direction and in the y direction, signal is bounded. Bounded means stopped because of the conductor walls, but in z direction, signal is not stopped. So this is a bounded structure, but this equation is valid for unbounded medium. Unbounded medium. Now remove here, for example, air medium is there, let us say. For that medium, sigma is 0, it is lossless medium. Now remove this conductor, remove this conductor, remove this conductor, remove this conductor. Now it is called unbounded air medium. For that medium, this is gamma square. Now if you put in x direction conductor walls, then because of x direction conductor walls, you have to add some term called kx. K means constant, x means some constant is to be added due to x direction conductor walls. Similarly, ky means constant due to y direction conductor walls is to be added here, square square square, because this one is gamma square. This is gamma square, and now this is called gamma of the waveguide. Then square, in square form they are there, squares. That means for the waveguide there is a lossless dielectric medium, or otherwise lossless air medium here. For that medium, this is the gamma square, and that one plus you have to add one constant for x direction conductor walls, another constant for y direction conductor walls you have to add. For example, if you close this conductor wall also like this, then in the z direction also you have to add the constant, that is called cavity. We will talk of that later on. Cavity, that is called. Cavity means inside hollow. For example, if I close this wall like this, inside hollow is there. So here EM wave is actually EM energy is stored there. How it is stored? Because if I close the every side, here medium is there. That medium has epsilon. In that epsilon, electric energy is stored. In that medium has mu. Their magnetic energy is stored. Okay. Anyway, that is called cavity. Now what is this gamma square? And this is for unbounded medium. Why this constant in x direction is coming? Due to the walls in x direction. Why this constant in y direction is coming? Due to the conductor walls in y direction. Some term should be there here. So now this is called the what do you say, gamma g means a propagation constant of the guide. There are in the whole square forms. Now what is gamma square? This one, omega square mu epsilon kx square ky square, like this. Now finally I am telling this is a propagation constant for waveguide. This waveguide has medium. For that medium, epsilon and mu is there. That epsilon and mu is there, and in that medium signal is going. That signal has frequency f. Now due to conductor walls, this kx is equal to m pi by a. M is integer, a is width of the waveguide in x direction. So ky is equal to m pi by b. So n pi by b, and n is integer and b is height in direction. And already you know, students, the unit of this gamma square is 1 by meter square. That means kx square unit also 1 by meter square. Then kx square unit is 1 by meter square. Kx unit should be 1 by meter. So you see here, pi no unit, integer no unit. This is a is meter, so 1 by meter. So ky also 1 by meter. So 1 by meter square, 1 by meter square, 1 by meter square, 1 by meter square. Without derivations, I told you. Now after that I will be doing derivations also. From the derivations also you get same thing. Strictly speaking, it is useless to do derivations. It is wastage of your time. But I will do one for TE mode. I will do derivation. After that we will not do derivation. So from the derivation also we get same things only. We are studying logically. इसके लिए इसको ज़्यादा दिमाग चाहिए ये पढ़ने के लिए. कोई बात नहीं, बाद में derivation भी बता दूंगा आपको. So now let us continue the discussion. Actually, student, for IES students, na, this is conventional question, 15 marks question. They will ask this, discuss the propagation characteristics, or otherwise discuss the concept of wave propagation in the waveguide. Then you have to do this derivation, whatever I am telling now. So, dear students, I will continue from here. In the if the medium is lossless, then for unbounded medium, this one. For a rectangular wave guide, due to x is equal to 0 comma x is equal to a, conductor walls kx and due to y is equal to 0 comma y is equal to a, y is equal to b, conductor walls ky constants are introduced. These constants are introduced. So if the medium between conductor walls of rectangular waveguide is filled with lossless dielectric or otherwise perfect dielectric. Why I am saying lossless dielectric? You know, already we have written for lossless case, we have written gamma square. That is why. with lossless dielectric, then gamma g square is equal to gamma square plus kx square ky square equation 2. So put equation 1 in 2. That means what is the difference between guide propagation constant and unbounded propagation constant? In unbounded propagation constant, kx by a, there is no conductor wall. So a is equal to infinity. Kx is equal to m pi by a. A infinity means you get kx 0 for unbounded medium. I am telling you kx is equal to m pi by a. For unbounded medium, assume that the conductor walls are at infinity distance. Infinity distance means you can never see that. That means there are no walls at all. So if you put a infinity, then kx 0 for unbounded medium in y direction. You assume that walls are at infinity distance. Then substitute b infinity. Then this is also 0. This is also 0. Then you get for unbounded medium. So put 1 in 2, then gamma g square is equal to minus omega square mu epsilon and plus kx square plus ky square. Let us say this is equation number 3. Now gamma g square omega square mu epsilon, you know why I already told you square is written, because entire equation is in square form. That is why it is 1 by meter square, 1 by meter square. Kx is m pi by a. Kx unit is 1 by meter. Whole square means 1 by meter square. That's why. These together, they are written as kc square. So this is equation number 4, where kc square is equal to kx square plus ky square. So kc is equal to root of kx square plus ky square. So this is equation number 5. Now, dear friends, actually kc square is equal to kx square plus ky square. Kx is m pi by a and ky is n pi by b. Some rough work I am doing here. I am explaining something for you. Once if you select the waveguide, student, and then a is equal to 2 centimeter is taken, b is equal to 1 centimeter is taken, then a, b are fixed now, then almost this value mode also fixed. For example, I want to send a signal in TE11 mode, then m is 1, n is 1. don't worry सर मोड क्या डिस्कशन चल रहा है, थोड़ी देर में समझ में आएगा, थोड़ा समझ में आ जाएगा, little bit you will understand, don't worry. Mode also I will explain, don't worry. So m is equal to 1, n is equal to 1, then that is called T11 mode. So then automatically m value constant, n value constant, a, b constant, pi also constant, kc is constant, student. Once if you select the rectangular waveguide, then you will be sending energy through particular mode. Mode means the way you carry the energy, or otherwise the way you carry the power. Later on we will see that. Then kc is constant, student. Then if you select the air medium, then epsilon is equal to epsilon naught, mu is equal to mu naught. So this is also constant, this is also constant. But what is W? 2 pi f. What is f? The input signal frequency, you can send f is equal to 10 gigahertz frequency, you can send f is equal to 1 gigahertz frequency. That is called operating frequency. The operating frequency means the frequency at which you are sending the power. So where f is variable. Now for example, I got kc square is equal to 10. Then mu epsilon some value is there. Then keep changing frequency in such a way this value is negative, this value is positive, and both become equal, and so that gamma g is equal to 0. That will happen only at particular frequency. Okay, students. So I will do like this, student. Omega square mu naught epsilon naught plus kc square is there for this gamma g square. Now this is omega square. 1 divided by root mu epsilon is 3 into 10 to the power 8. So plus kc square, let us say after solving I got some value, let us say 5 like that. Now I will change this omega in such a way this value 5 and this value becomes minus 5, then overall value becomes 0. So that happens only at a single frequency, that is called FC, cutoff frequency. So dear students, now what I am telling you, till now what I have explained, for a waveguide this is constant for particular mode, and this also constant, this is variable. Keep changing this f in such a way at particular frequency called f is equal to fc, or otherwise omega is equal to omega c, this gamma g becomes 0. So I am writing this, let at omega is equal to omega c frequency, this is angular frequency, angular frequency, equation 4 becomes 0. Then you substitute that minus omega c square mu epsilon plus kc square is equal to 0. So kc square is equal to omega c square mu epsilon, and say this equation number 6, kc is equal to omega c root mu epsilon, this is 7. This is also very important, student, this one in circular waveguide also you have to remember. I will tell you, don't worry. This kc, c means cutoff. Why it is called cutoff? Because that is going to define fc called cutoff frequency. That is why it is called cutoff. Once again, student, this kc value decides the omega c means 2 pi fc, where fc means cutoff frequency. We will discuss that also. So that is why this kc value decides the fc. That is why it is called cutoff. So I already told you in uniform plane wave, beta or otherwise k, both are exchangeable. Beta means phase shift constant or otherwise wave number. K means phase shift constant or otherwise wave number. Kc means cutoff phase shift constant or otherwise cutoff wave number. So here that is the kc formula. Every student has to remember that omega c into root of mu epsilon. In circular waveguide also I will write this, where kc is cutoff wave number, that is nothing but beta c only, student, beta c, or otherwise I will write here. Okay, you write there, no problem. Cutoff wave number or cutoff phase shift constant. Student, beta is equal to omega root mu epsilon. Beta c means omega c root mu epsilon, that one only. So kc is equal to beta c, that is equal to omega c root mu epsilon, student. So once again I am telling, beta is equal to omega root mu epsilon, student, that is nothing but k only. Beta c means omega c root mu epsilon, that is called as kc. But I told you in some books they what do you say, they talk in terms of beta, and some other books k. So cutoff wave number, you remember this one and remember this one. Of course, if you want you can put this also, because I want to tell you beta and k both are same. Now put equation 7 in. Anyway, we will do some mathematics here. Yeah, we will do some mathematics. So equation 7 implies omega c is equal to this one, 1 by root mu epsilon, okay, under root kc, right? Then this is equation number 8. So kc is written here, equation 5. Put 5 in 8. So omega c is equal to 1 by root mu epsilon, and root kc, actually any print mistake is there here? Student, why I put root here? No root na? Yeah, 1 by root mu epsilon, no root here na. Okay. So now put equation 5, that is kc, in equation number 8. So here kc is nothing but root of kx square plus ky square. So this one is 9. For rectangular waveguide, kx is equal to m pi by a and ky is equal to n pi by b. So now this equation becomes omega c is equal to 1 by root mu epsilon and m pi by a whole square and n pi by b whole square. Now this is 2 pi fc. So fc becomes 1 divided by 2 pi root mu epsilon and m pi by a whole square and n pi by b whole square. Okay. See, students, here m is integer, n is integer. I will tell you the meanings also later on. If any doubts are there for you, some names, etc., they will be clarified while discussing the subject. Don't worry. So here it is called as FCMN. That means cutoff frequency. C means cutoff. F means frequency. Cutoff frequency for MN mode is equal to 1 by 2 pi root mu epsilon, and this is m pi by a whole square plus n pi by b whole square under root. This is one thing. Now 1 by root mu epsilon is called as v. So v by 2 pi. So m pi by a whole square plus n pi by b whole square. Now pi, this pi square is there. It comes out of the root pi. Pi cancel. So v by 2 root m by a whole square plus n by b whole square. This is FCMN, student. And here in some books you see the formula in this form, mu epsilon form. And here also pi is there, here also pi is there. In some books you see this in velocity form. And pi is there, pi is there. In some books you see velocity form, but no pi here. Here also no pi. So any one of the form is used. So you should not confuse. So where v is equal to where anyway we will be writing this later on in the note now. So FCMN is called cutoff frequency for MN mode, dear students. Anyway, why it is called cutoff frequency, after some time we will understand, because that decides the wave propagation. That is why. If operating frequency is more than this cutoff frequency, then only the signal is transmitted. Otherwise, signal is not transmitted. If operating frequency is equal to the cutoff frequency or less than cutoff frequency, then that signal cannot be transmitted through the rectangular waveguide. So this cutoff frequency decides which frequencies can be transmitted, which cannot be transmitted. That is decided by this frequency. So that is why it is called cutoff. So it is like in examination, pass marks, cutoff marks are there. Like that only this is also. Now one important observation: who decides this cutoff frequency? Otherwise, the cutoff frequency value is decided by whom? कौन decide करेगा ये cutoff frequency को? Answer: waveguide dimensions, and inside the waveguide medium parameters. For example, inside the waveguide dielectric is there, for that mu epsilon value is there here. Then waveguide has a width and B width, B height, they decide the cutoff frequency. So cutoff frequency depends on um, um, the medium parameters as well as waveguide dimensions. Okay, that means this cutoff frequency is no way decided by the person who is sending the signal. So the cutoff frequency is decided by the waveguide dimensions, and inside the waveguide medium is there. That medium parameters decide the cutoff frequency. Right, students? Now here equation 6 you substitute in equation 4. That means substitute kc square in terms of omega c square mu epsilon. In terms of omega c you substitute. So put 6 in 4. Put equation 6 in equation number 4. Then gamma g square is equal to minus omega square mu epsilon. Then kc square is nothing but omega c square mu epsilon. From this you pull out the omega square mu epsilon, or otherwise I will pull out minus omega square mu epsilon. If you pull out 1 minus omega c square mu epsilon, and omega square mu epsilon comes. So correct na? Next, minus omega square mu epsilon common, so you got this one. Mu epsilon cancel. This is 2 pi fc, then this is 2 pi f, so 2 pi cancel, so fc by f whole square you get. Now gamma g is equal to plus or minus j omega root mu epsilon, because root you take na, minus 1 is j square, so plus or minus j root. Minus 1 is j square, root of that is plus or minus j, then omega square root is omega mu epsilon, root mu epsilon. Okay, here you got 1 minus fc by f whole square, you have to take root for that. Okay, now this is gamma g j omega root mu epsilon 1 minus fc by f whole square, where omega is 2 pi f, omega c is 2 pi fc, students. Now you got gamma g equation in terms of fc. So fc is this one, and f is operating frequency. Here omega is 2 pi f, this f and this f both are same. Here f and here f both are same. Now case 1, student. Case 1. What happens if f is equal to fc? That means here f is operating frequency. Operating frequency means the frequency at which you are sending the signal. So operating frequency. fc is cutoff frequency, already I wrote here. Later on also we will see that one. If f is equal to fc, then gamma g is equal to 0. Gamma is actually alpha plus j beta, and gamma g means alpha g plus j beta g. Now from this you got alpha g 0, attenuation constant alpha means g means waveguide, so phase shift constant beta means g means waveguide, both are 0. So in this case alpha 0 beta 0, there is no wave propagation in this case. So there is no wave propagation. Already we have studied in the uniform plane wave as well as transmission line, alpha 0 and beta should not be 0, then only wave propagation exists. So in this case, there is no wave propagation. Next, students, F less than Fc we will put. I will write that as case 2. Case 2, student. So if operating frequency F is less than the cutoff frequency, okay, so if F less than Fc, then what will happen? Let us see. That is case 2. If F less than Fc, student, that implies Fc by F is greater than 1, right now. Then gamma g is equal to j omega root mu epsilon root of 1 minus Fc by F whole square here, plus or minus. So Fc by F value is greater than 1, then greater than 1 whole square is again greater than 1. 1 minus greater than 1 is negative. For that, what I do? I will write this like this. Minus of Fc by F whole square minus 1. So it is correct now. Now if you see, don't bother about this minus. Fc by F is greater than 1. The Fc by F whole square is also greater than 1. Greater than 1 minus 1 becomes positive. So this term is positive. The minus is there here. If I get this minus outside, this minus 1 is j square and it comes outside, j into j square is minus 1. That becomes real actually. So plus or minus j omega root mu epsilon, that becomes this gamma g is alpha g plus or minus j beta g, and this is nothing but plus or minus omega root mu epsilon root of Fc by F whole square minus 1, student, because minus 1 is j square, it came out, it has become plus minus j into j square minus 1. Anyway, you got real, that is important. If you compare both sides, this has become real, student. Now alpha g is equal to omega root mu epsilon root of Fc by F whole square minus 1, and beta g is equal to 0. In this, first of all, there is no wave propagation because beta 0. Even if wave enters into the waveguide, there is an attenuation. There is an attenuation, student. So there is an attenuation here. So in this case, there is no wave propagation, or otherwise, even if wave enters, attenuation is there. So this is called evanescent mode. In English, evanescent means decrease, or otherwise decay. So evanescent modes it is called as. So dear students, this alpha g also should be remembered, student. How you remember this, I will tell you after some time. Beta g you are going to remember. For beta g, this term is reversed, then this becomes alpha g. So here, in this case, there is no wave propagation, or otherwise there is an attenuation. There is an attenuation. So this is called evanescent mode. Evanescent means decay or otherwise decrease. Evanescent mode this is called as. Case 3. If f greater than fc, of course students, then fc by f is less than 1. Then gamma g is as usual plus minus j omega root mu epsilon root of 1 minus fc by f whole square, and this one is alpha g plus j beta g, of course plus or minus here, is equal to plus or minus j omega root mu epsilon root of 1 minus fc by f whole square, students. Okay. Now ultimately alpha g is equal to 0 here. That's what we want. No attenuation. No attenuation. And then beta g is equal to omega root mu epsilon root of 1 minus of fc by f whole square. So here beta is there. Beta means phase shift constant. G means guide. Phase shift constant of the waveguide. In this case, EM wave is transmitted. EM wave is transmitted without attenuation. Without attenuation. This is what we want. So conclusion is, case 1 f is equal to fc, there is no wave propagation. Case 2 f less than fc, here also there is no wave propagation. That is why in a waveguide, if f less than or equal to fc, then there is no wave propagation. Only case 3, if operating frequency is greater than the cutoff frequency, then only wave propagation is possible without attenuation. If f less than or equal to fc, then alpha present, because of attenuation, signal cannot be transmitted in the waveguide. That is why I told you it is high pass filter. It can transmit the signal only if f greater than some cutoff frequency. So that is why it's called high pass filter. So after this, we will take the TE mode. We will define the we will give the definitions of the modes like TEM mode, HM mode, and TE mode, TM mode. Then we will solve the equations for TE mode. Strictly speaking, we should study this without doing derivations like this. We should study. Anyway, for one case, I will do the derivations. Okay.